This video contains the solutions to the tutorial problems for topic 10. Problem 1. In this problem we're asked to sketch the magnetic field lines around different combinations of magnets. So the first one is just a plain bar magnet. So in order to sketch the magnetic field lines we need to draw them coming out of the North Pole and into the South Pole. And the magnetic field lines do go through the middle of the magnet like this. So that's one of the magnetic field lines. And then on the other side, so that it's symmetric. Out of the North Pole and into the South Pole. And then we could add some more if we wanted, but that shows the magnetic field lines around a single magnet. Now around two magnets like this, we have them coming out of the North Pole, and the lines coming out of these two magnets don't cross. Magnetic field lines never cross, but they repel each other like this. And so we can draw these wrapping around and going back in the South Pole. So out of the North and into the South. Try to draw them so that they don't cross each other, remember. And out of the North. And so here you can see that they're bunched up so that they've got more of a vertical component than they would if this other magnet was not here. So that's what they look like around configuration B. And now around configuration C, they go from the North Pole to the South Pole here between the magnets. So this is like having an extra long bar magnet. So we might have some coming out like this. And these ones here just go all the way through. Out of the North Pole and into the South Pole. And so that shows the main features for this combination of magnets. And finally, for this solenoid, now what we're going to need to do is use our right-hand screw rule to work out which way it goes. So we've got the current flowing up the outside here. So wrapping your fingers round, your thumb then points towards the North Pole. So this end here is acting as a North Pole, and this end here is acting as the South Pole. And so the magnetic field lines look the same as for a bar magnet, like this. And so this looks just like the bar magnet with a north pole up here and a south end down here. Problem 2. In this problem we have a bottom magnet that has a north pole on the top and a south pole down the bottom, and we're going to pull this magnet apart. So let's put our two pieces of the magnet apart like that. And the question then asks us, if we crack it like this, will the two halves attract each other, repel each other, or not interact? Okay, so let's have a think about this. Now what we've got still is a north pole up the top of each magnet and a south pole down the bottom. And when we pull them apart, we've still got a north pole up here and a south pole down here. So these two north poles are going to repel each other. These two south poles are going to repel each other. So this one's going to try and move this way. And so this magnet is going to, the two halves of the magnet are going to repel each other. Okay, next part of the question. Okay, now we're going to crack our magnet in the opposite direction through the large circular face. So let's move these two parts of the magnet apart. So when we move this one apart, we'll have a circular magnet down there. Now, up here, we've got the north pole of this magnet. And so when we split this magnet in half, we're going to get a south pole developed down here. And down the bottom we have a south pole here, and so we get a north pole up here. So now we've got a south and a north pole next to each other. So these magnets are going to feel a force towards each other, which is exactly what we saw in the lecture when we broke the magnet in half. So part C of this question says, what are the implications of this if you want to build a very strong magnet? Well, depending on how you break the magnet, it means that if you have a very strong magnet, if you shatter it, some bits are going to feel a large repulsive force and some bits are going to feel another large attractive force. So it means that if you have a very strong magnet, and you shatter it, some parts are strong so this can cause a strong magnet to explode. So it's just a bit of an OH and S issue that you need to be aware of if you ever deal with these really strong magnets. Problem 3. So for this problem you need to watch a little video which tells you about how the sun's magnetic field's about to flip, and then you're asked to compare and contrast the sun's and the Earth's magnetic fields. So in the sun, it has magnetic fields generated by flowing currents in the gas, but the sun's a bit different because it's not a solid object. The center of the sun actually rotates a lot faster than the edges of the sun up here, the top and the bottom. And so the magnetic field lines within the sun get twisted. And so every 11 years, this twisting gets so much that the sun's magnetic field flips and resets itself. So the sun has an 11-year cycle, and it's very regular. The Earth, on the other hand, we're not 100% certain what causes its magnetic fields to reverse, but their flips are not regular, happen approximately every 450,000 years. So the Earth has a much longer cycle, and the cycle's not at all regular, unlike the Sun. Now, another thing that we can compare is the strength. At the photosphere, the top of the Sun's magnetic field is approximately 50 to 400 microteslas. The Earth's magnetic field is about 25 to 65 microteslas, depending where you are on the Earth. So the magnetic field strength isn't that different, but the cycle is very different. So it'd be a good idea to keep your eye on the news to see what some of the results of the Sun's magnetic field flipping is. There's likely to be some effect on electrical components, especially on spacecraft and things which aren't protected by the Earth's magnetic field. Problem 4. So in problem 4, we're told that in Sydney, the horizontal component of the Earth's magnetic field is 25,000 nanoteslas and the vertical component is 51,000 nanoteslas. First of all, we're asked to calculate the total magnetic field strength in Sydney. So what we need to do this is add the horizontal component and the vertical component. So the horizontal component was 25,000 nanoteslas. The vertical component was 51,000 nanoteslas, and so we add these two like that, that's 90 degrees, and so we can use Pythagoras' theorem to get the total magnetic field. Now let's just check that if the vertical component is going to be going up or going down. Remember, here's our Earth, here's Australia, here's Sydney, and we've got a North Pole down here and a South Pole here. So magnetic field lines tend to go like this, and so we'd expect them to be coming up out of Sydney, so that's why we've given it an upwards vertical component rather than downwards. And so this will be pointing towards the North geographic pole. And so to work out this magnitude, we can use Pythagoras' theorem. We've got 25,000 squared plus 51,000 squared, and solving that on the calculator, we get 57,000 nanoteslas. And we just give it to two significant figures here because these are both to two significant figures. Now part B asks us to work out this angle here. And so we can use SOHCAHTOA. And we've been given the opposite and the adjacent. So we'll use tan theta is equal to opposite, which is 51,000, over the adjacent, which is the 25,000. So this tells us that theta is equal to 64 degrees. And now part C asks us, would you expect the magnetic field strength in Darwin to be stronger or weaker than in Sydney? Okay, so here we've got the magnetic field lines coming up like that. Above Darwin, we'd expect them to be more horizontal, less vertical. And remember how around a bar magnet, there's less magnetic fields in this region than there is in this region. So Sydney's more like in this region, Darwin's like being in this region. So we would expect the overall field to also be weaker. So vertical component should be much less. Horizontal, well, it will be similar or more. And the overall would expect it to be smaller. So that's probably what we'd expect. In actual fact, the total field at Darwin is equal to 46,000 nanoteslas, so that is less than the 57,000. It is a bit weaker. The horizontal is equal to 35,000 nanoteslas. So the horizontal component is stronger because we've pretty much a lot more of the field is in the horizontal direction here than it is here, and the vertical is equal to 30,000 nanoteslas as opposed to 51,000 nanoteslas at Sydney. So the vertical component is quite different. Problem 5. A proton enters a particle accelerator with a speed v is equal to 6.0 times 10 to the 6 meters per second. The proton enters a region with a magnetic field strength of 0.35 teslas. So let's draw that here. It doesn't tell us the direction, so we can choose any direction. Let's draw it like this. So this is 0.35 teslas. The magnetic field makes an angle of 30 degrees with the velocity of the proton. Okay, so here's the velocity of the proton, and this angle in here is 30 degrees, and we've got the size of the velocity here. So part A says sketch a diagram clearly showing this information. So we've done that already. So that's the answer to part A. Part B, calculate the force acting on the proton. So in order to calculate this, we're going to need to use F is equal to B QV sine theta. And so we can just substitute in. B is 0.35 teslas. Q, now that's the charge on the proton, which has the same magnitude as the charge on an electron, so it is equal to 1.602 times 10 to the minus 19 coulomb, times the velocity, which is 6 times 10 to the 6 meters per second, times sine 30. So now we just need to enter this into the calculator and solve it. When we do that, we get 1.68, which is 1.7 to two significant figures, times 10 to the minus 13 newtons. And now we should give a direction as well. The direction is going to depend on how you've drawn your diagram. If you've drawn the diagram the same way as I have, then line your fingers up with the magnetic field, your thumb points in the direction of the velocity, and you can see that your palm is going into the screen. So the force is into the screen using the right hand rule. So into the screen, but this direction does depend on how you've drawn your diagram. Part C says calculate the acceleration of the proton. And so to calculate this, we're going to have to use Newton's second law. F is equal to ma, which tells us that the acceleration is equal to the force over the mass. So we've calculated the force here. We got 1.6821 times 10 to the minus 13. We'll keep all the significant figures in to do our calculation and then get it down to the two significant figures at the end. Now this is a proton, so we need the mass of the proton, which is 1.673 times 10 to the minus 27 kilograms. And so solving this one on the calculator, we end up with 1.0 times 10 to the 14 meters per second, and it's in the same direction as the force, so into the screen. But that direction again depends on how you've drawn your diagram. Now part D asks us how would the force and acceleration compare if the particle were an electron rather than a proton. Well, the force, we have exactly the same magnitude charge, just opposite charge. And so BQV sine theta is going to work out to the same value, but with the opposite sign. So force will have the same magnitude, but an opposite direction. So in this case, it would be out of the screen. Now the acceleration, on the other hand, acceleration is equal to F on m, and our m is now much smaller, and so we would expect our acceleration to be much larger. So we can calculate it, 1.6821 times 10 to the minus 13, and then the mass of an electron is 9.109 times 10 to the minus 31 kilograms. And so solving this on the calculator, we get 1.8 times 10 to the 17 newtons. and it's also in the opposite direction, and so this is out of the screen. So much larger and in the opposite direction. Problem 6. In this problem, we're asked about a mass spectrometer, and we start off by shooting in something with, let's call it mass 1 is equal to 11.65 times 10 to the minus 27 kilograms, and the magnetic field is initially set to 0.283 milliteslas. And when we shoot it into the magnetic field, it feels a force, and so it follows a circular path like this. And then we shoot another isotope in which has a higher mass. Mass 2 is equal to 16.63 times 10 to the minus 27 kilograms, and we're asked if this mass here undergoes the same circular orbit so that it comes to the detector, which is the same distance away, then what is the strength of the magnetic field for this same particle here? Now, some things stay constant between these two cases. We have R1 is equal to R2 is equal to, let's just call it R, the radius of the circular path, and we know that the charge is not changing because it remains singly ionized, so with a charge E. Okay, so what we need to do is work out B2. So we know that this circular motion is caused by the force from the charged particle moving in the magnetic field. So we know that M2 V2 squared on R, so that's the centripetal force, is equal to B2 Q V2 sine theta, and that's sine 90, so we can forget that sine theta. And so we can solve this to work out what B2 is. It tells us that B2 is equal to, this Q here is equal to E, so let's replace that with an E, and we've got B2 is equal to, that we'll cancel one of those, M2 V2 over RE. And we know what M2 is, we're given that. So what we need to do to work out what this is going to be is find V2. So V2 is equal to what? Well, in order to work out V2, we can look at its relationship to V1. We know that they go through the same accelerating voltage, and so we're told that F is equal to MA is equal to QV, and this thing is constant. Now what we can do is use some of our laws from mechanics. So we know that V squared is equal to the initial velocity squared plus 2AS, and this is the distance that it goes through that accelerating potential difference for. So if we assume it starts from rest, then we've got V2 squared is equal to 2AS, where S is the distance, and so it's not changing for these two cases. And we know that the acceleration is equal to the force over the mass, so this is equal to 2F on M2S, and this stuff here is all constant between the two cases. We're told that the force is constant, and this is the distance over which it accelerates, which is fixed. And so we know that we could do the same thing for velocity 1. So we've got that velocity 1 on velocity 2 is equal to the square root of 2fs on m1 over 2fs on m2. These cancel because they're constant, and we've got the square root of m2 on m1. And so this tells us we're trying to find V2, so we've now got V2 is equal to V1 root M1 on M2. And now we have M1, we have M2, but we still don't have V1. But we can calculate V1 by realizing that in the initial case, we've got that the centripetal force, which is M1 V1 squared on R, is caused by the magnetic force. So that's V1Q, which is E, V1 there, and so these cancel out, and so we have V1 is equal to B1 on M1 ER, and so we've now got V1, which we can put in here. So we have V2 is equal to B1 on M1 ER, square root of M1 on M2. This will cancel with that, and so we will end up with B1 ER over the square root of M1 M2. And now we've got V2, and so we can go back up here, and we've got B2 is equal to M2 over RE times V2, which is B1 ER over the square root of M1 M2. These ERs are constant, so they cancel out, and we've got this is equal to B1 times the square root of M2 on M1. And so now these are all things that we have numbers for up here. So finally now we can just substitute in. B1 is equal to 0.283 times 10 to the minus 3. Now when we divide these masses, we can leave off the times 10 to the minus 27 because that's just going to cancel out. So we'll end up with 16.63 over 11.65. And so solving this on the calculator, we end up with 0.338 milliteslas. So we've left off this times 10 to the minus 3, but given it as milliteslas. And so let's just have a think about this. This second particle is heavier. If it's heavier, it's going to need more force in order to make it turn. So to have more force, it's going to need to have a stronger magnetic field. And we have got a stronger magnetic field like we would expect. So it seems like that is a reasonable answer. Problem 7. Horizontal wire with a length of 0.50 meters long is placed in a uniform magnetic field. When the wire is horizontal, it experiences no force when a current of 7.5 amps flows through it. Now if it's feeling no force and it's a current carrying wire in a magnetic field, because F is equal to BIL sine theta, it means this sine theta term must be 0, i.e. the magnetic field and the current must be parallel. So let's draw the magnetic field here in blue. So we can have the magnetic field either going to the right like this, or it could alternatively be going to the left. But that's what our magnetic field looks like there. And now the wire is tilted upwards at an angle of 19 degrees. So this is 19 degrees here. And now it feels a force of 4.4 times 10 to the minus 3 newtons. And we're asked, what's the strength of this magnetic field here? And so we can use F is equal to BIL sine theta and rearrange it for B. So B is equal to F over IL sine theta. And so the force in this case is 4.4 times 10 to the minus 3 newtons. The current is 7.5. The length is 0.50. And the angle between the field lines and the current is equal to 19 degrees. So this is sine 19. And so we can now solve this on the calculator, and we get 3.6 times 10 to the minus 3 teslas. That's to two significant figures. And so we can write this as 3.6 milliteslas. This is problem 8. Now in this problem we have a copper rod with a length of 0.85 meters. And it's on a frictionless table. Each end of the rod is attached to a wire by an unstretched spring that has a spring constant K is equal to 75 newtons per meter. A magnetic field with a strength, so this field has the strength 0.16 teslas, is coming out of the page. And we're asked in part A, in what direction must the current flow in order for the springs here to stretch? So in order for the springs to stretch, we need to have a force in this direction. So what we can do is use our right hand rule. So you line your fingers up coming out of the screen, because that's the direction the magnetic field is going, and your palm is facing downwards. So you can see that your thumb then points in this direction. So the current is flowing from the left side to the right side. Now in part B, we're told that if the current has a magnitude of 12 amps, so I is equal to 12 amps, we need to work out how much the string stretches. Well, we can start by working out what this force is, the force due to the current flow. So we know that F is equal to BIL sine theta, and B is 0.16, I is 12, and L is 0.85, and then sine, the angle between the magnetic field and the current is 90 degrees, so that's sine 90, and this thing is 1. So solving that on the calculator, we end up with a force of 1.632 newtons. And now this force goes into stretching both these springs. So we only get half of the force applied to each spring. Now for stretching a spring, we know that the spring force, F, is equal to minus kx. And so this spring force, it acts in the opposite direction, and this spring is going to stretch until these two forces are in equilibrium. So it will stretch until we have kx is equal to the BIL, which is the 1.632, but only half of that force is going into each spring. And so we have that x is equal to 1.632 over 2 times k, and k is 75. So solving this on the calculator, we end up with 0.011 meters, or we can write as 1.1 centimeters. Problem 9. In this problem, we're told that wire 1 carries a current of 15 amps and wire 2 carries a current of 12 amps. And in the direction shown. And first of all, we're asked to calculate the magnetic field at position X. So to answer this, we're going to need to use the formula B is equal to mu naught I over 2 pi r. So let's start by calculating the magnetic field at X due to wire 1. So let's call that B1, which is equal to mu naught I1 over 2 pi r. So this is 4 pi times 10 to the minus 7 times 15 over 2 pi times the distance, which is the 0.050. This 2 pi will cancel with that, and we'll be left with a factor of 2 there. So then entering this into our calculator, we get 6.0 times 10 to the minus 5 Teslas. And now let's just look at the direction. Using your right hand screw rule, if you point your thumb in the direction the current in wire 1 is going, then you can see at X, this is going to be going into the screen. And now what we need to do is calculate the magnetic field here due to wire 2. So that's B2, which is just equal to mu naught I2 over 2 pi r. And so that is equal to 4 pi times 10 to the minus 7 times I2, which is the 12 amps, over 2 pi times the distance here. Now if this is 0.1 meters and this is 0.05, then this here is also 0.050 meters, so 0.050. And solving this on the calculator, we can cancel out those pi's to save some time. We get 4.8 times 10 to the minus 5 Teslas. And now with the right hand rule, your thumb is now pointing towards the left, and you can see at X, your fingers are pointing into the screen. So to get the net magnetic field, both these magnetic fields are acting in the same direction, so we just have to add them together. So we've got 6.0 plus 4.8, or times 10 to the minus 5 Teslas. So solving that on the calculator, we get 1.1 times 10 to the minus 4 Teslas into the screen. And that's to two significant figures. Now part B asks us to calculate the magnetic field at Y. So we use exactly the same technique here, and you'll notice that Y is the same distance from wire 2 as X is. So we already know the magnitude of B2. It will be equal to 4.8 times 10 to the minus 5 Teslas. But using our right hand screw rule now, you can see that if your thumb is going to the left, then at Y your fingers are pointing out of the page. So this is out of page. And B1 is equal to mu naught, so 4 pi times 10 to the minus 7 times I1, which is 15, over 2 pi. And now the distance, we've got 0.05 plus 0.05 plus 0.05, so 0.150 meters. And so cancelling those factors and then solving it on the calculator, we end up with 2.0 times 10 to the minus 5 Teslas. And with the right hand rule, you can see that it's got the same direction as it had up here. So this is into the screen. And so B net, in this case they're acting in opposite directions. The out of the page is larger, and so we're going to end up with a net magnetic field out of the page. We'll have 4.8 minus 2.0 times 10 to the minus 5 Teslas, which is equal to 2.8 times 10 to the minus 5 Teslas out of the screen. Okay, and finally C, we're asked to calculate the force per meter of wire 1 due to wire 2. And so we know that the force is given by mu naught I on d I1 times I2 times the length. And so we can just substitute in. We've got 4 pi times 10 to the minus 7. I1 is 15, I2 is 12. This is over a separation of 0.100. And this is per meter, so the length we're considering is 1 meter. And so solving this, we get 3.6 times 10 to the minus 4, and that's newtons per meter. And we should just consider these currents are going in opposite directions, and so this is a repulsive force. So let's just note that that is a repulsive force there. This is problem 10. Now in this problem we've got two wires which are shown in this diagram. They both carry a current I is equal to 55.0 amps. And one of them, this one is carrying it into the page, and this one here is carrying it out of the page. And we're asked to work out what the magnetic field is at this point P here. What we're going to need to do in order to do that is work out the magnetic field due to each of these wires individually at point P and just add them together. So we know that we have that the magnetic field lines form a circle around the wire. So we can see that at this point P here, with this going into the page using your right hand screw rule, the magnetic field lines are going around this circle like this. And so at P, the contribution to the magnetic field is down here like this. So this angle here is 90 degrees, and this is B down here due to this wire here. So it's just a tangent to the circular magnetic field line. So let's have a look at this second one now. This second wire is carrying the current out of the page. So draw a circle around there. And then you can see that the magnetic field line again is a tangent, and it forms an angle here of 90 degrees. Now let's just work out the direction, because this is coming out of the page. Wrapping your fingers round, they're going in this direction, and so this is going down like this. And so that's the B due to the second one. And now what we can do is work out the magnitude of these B's, and then we're going to need to add them together as vectors, so join them together head to tail. So in order to work out the magnitude, we know that B is equal to mu naught I over 2 pi r. Now in both these cases we've got the same current and we're the same distance from the wire. So they're actually going to have the same magnitude. We can substitute in. We've got 4 pi times 10 to the minus 7 times 55 over 2 pi times 0.100. This 2 pi will cancel with that 4 pi, leaving it 2. And so this gives us a magnitude of 1.1 times 10 to the minus 4 Teslas. So each of these B's has the same magnitude. But now what we need to do is we really need to think about how to add them together. So let's draw this blue one here. So here it is. Let's split it into a horizontal, that's the vertical, and here's the horizontal component. So this is 1.1 times 10 to the minus 4 Teslas, and this angle in here is theta. Now let's just have a look at the geometry in this situation. Okay, so you can see this is an equilateral triangle. All the sides have the same length. So in this triangle, this angle here is 60 degrees, this angle here is 60 degrees, and the angle up here is 60 degrees. And this vertical component is bisecting this angle, splitting it in half. So that's 30 degrees there, and that's 30 degrees there. So this here is our B vector, which we've drawn there. This angle here is 30 degrees, and the tangent, which is here, and the radius here make an angle of 90 degrees. So that's 90 degrees with that being 30. So this angle in here has to be 60 degrees. So this angle here is 30 degrees. So this side here has a magnitude B cos 30, where B is this number here, and this side here has a magnitude B sine 30. And now what we're wanting to do is add this other B to it, the pink B, so that they're added head to tail. So here's the head of that one, here's the tail of this one, and once again we can split it into horizontal and vertical components. In this case, this one here is going down like this, and so we've got this vertical component here. And now the geometry in this situation turns out to be exactly the same. It's very symmetric. It's just a mirror image of this one here. And so we've got the same but opposite horizontal component here. While the green arrow is going that way, the pink one is going in this direction here. So these horizontal components cancel each other out, while these vertical components add together. So again, we've got 30 degrees there. This B has the same magnitude, 1.1 times 10 to the minus 4. So here we've got B sine 30. So this tells us that our net magnetic field is equal to the sum of these two. So this is 2B sine 30, and that's going down the page. And so that's equal to 2 times 1.1 times 10 to the minus 4 times sine 30. And that is equal to 1.1 times 10 to the minus 4. And so this is the net magnetic field. And so this is the magnetic field at P, 1.1 times 10 to the minus 4 down the page.